All right. So we're still talking about solving systems of linear differential equations and kind of how that all plays out. Um, I always like when the date makes a nice equation. 5 times 5 is 25. Feels good. All right. Well, you probably wouldn't be surprised how often my brain thinks of things like that. So I was like, oh yeah, 6 plus 1 is 7, something like that. That's my anniversary. June 1st, 2007. 6 plus 1 is 7. But that's how I remember things. Um, so let me ask real quick. So for those of you in Lee's class, you all started talking about complex eigenvalues and eigenvectors. Okay. And for those of you in Varn's class, have you started talking about this stuff yet? Okay, cool. All right. So obviously we're not quite in the same spot, but you guys will certainly catch up to where we're at. Um, I feel like so let me ask you all another question. For those of you in Lee's class, did he start talking about, or has he talked about how you can classify the sorts of shapes of your solutions based on the eigenvalues? Like whether you have a node or a spot. Okay. So we'll kind of talk about that and then we'll jump around a little bit. So let's talk about classifications of stability. I would actually say classifications of the equilibrium. And so as a reminder, the kind of general setup is the following. We're looking at a system of differential equations, something like dx1 dt equal to some multiple of x1 plus some multiple of x2, and dx2 dt equal to, again, some c times x1 plus some d times x2. So that you can rewrite this system of equations as the derivative of the vector x equal to the matrix A times the vector x, or written actually as vectors, the derivative of x1 with respect to t, the derivative of x2 with respect to t, equal to the matrix A, B, C, D, where A, B, C, and D are all just nice constants, times the vector x. And the idea here is that we are finding solutions to this. And we've already talked about what the solutions are going to look like every time. Well, they're a little bit more complex when the eigenvalues are imaginary. Ha 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 ha. But they're still the same idea. They just have it's a little bit more figuring out what's going on when the eigenvalues are complex. But the solutions are always going to look like the following. It's always going to look like x as a vector as a function of time is equal to c1e to the lambda 1t times v1 plus c2e to the lambda 2t times v2. And then I would remind you that when you find this, it's really, so this way of writing it is really two solutions. Your vector x1 of t, x2 of t is equal to c1 e to the lambda 1t times whatever your first eigenvector is. I don't really have great notation for this, so let's just call it, no, I don't really want to write anything there. I'm just gonna leave that blank, plus c2 e to the lambda 2t times whatever that second eigenvector is. So your first row of equations is x1 equal to c1 e to the lambda 1t times whatever that first entry is there, plus c2 e to the lambda 2t times whatever that first entry is there. And similarly, for the second equation for x2, it's c1 e to the lambda 1t times whatever is there, plus c2 e to the lambda 2t times whatever is there. I suppose I could use, I'll try and use some somewhat typical notation here. I'm gonna write this as v11 and v21, and this is v12, v22. There is a not terrible reason for that notation, but I wouldn't sweat it too much. We're usually just finding the numbers there, so don't worry about that a lot. So we've talked a little bit about how when we graph the solution to this, you get eigenlines and null lines. We talked about that on Friday a little bit. And specifically for the eigenlines, which are the lines that just point in the directions of your eigenvectors, if your eigenvalue is positive, we travel in the direction away from the origin, which is our equilibrium. And if our eigenvalues are negative, we travel in towards the origin. So here's what we're going to say. If both eigenvalues are positive, sorry, are negative is what I want to start with, are negative, then the equilibrium, which will be 0, 0, is a stable node, also called a sink. And the reason this is true is because if you were to give yourself some generic graph of the system here, and we just imagined our eigenlines were something like, here's one of the eigenlines, and here's another one of the eigenlines. Well, if both lambda 1 is negative and lambda 2 is negative, that means we are moving in towards the origin along those lines, which means no matter where we start, no matter what our initial condition is, we are always going to end up pointing in towards the origin, which is our equilibrium. So any starting place, like if I start here, still ends up pointing in that way. Or if I start over here, ends up pointing in that way, towards the origin. And I will say again, the reason this is true, right, is if your eigenvalues are negative, your e to the negative something times t is going to get closer and closer and closer to 0 as t gets larger and larger and larger. So the whole thing that's happening here is that as t goes to infinity, both x1 of t and x2 of t, whatever the x1 and x2 coordinates happen to be, get closer and closer to 0 as time goes on and on and on. So these go to 0, meaning no matter where we start, we get closer to the origin eventually. So long story, much shorter, eigenvalues both negative, stable node, meaning everything's just pointing inwards. On the flip side, if both eigenvalues are positive, then the equilibrium is an unstable node. Also called a source. And so again, if we had something, again, a very generic picture here with our eigenlines, it doesn't really matter how they look. Maybe I should say one thing that does matter though is however you draw your eigenlines, they should be going through the origin because they're always a vector that goes from 0, 0 to whatever the endpoint of the vector is. So they always go through the origin, but now everything is pointing away from the origin. Because both lambda 2 is positive and lambda 1 is also positive. So any starting point, any initial condition is going to push away, away, away from the origin. Here, as t gets really big, both x1 and x2 also get really, really big. And they could get positively big or negatively big depending on where you start. Right? Maybe you end up going down this way where x1 is really, really positive, and x2 is really, really negative. But the point here is that they're not getting closer to the origin, right? They're moving far away from the origin. And then I was going to say lastly, but it's not really lastly. It's the last possible thing that can happen if both eigenvalues are real. So if one of the eigenvalues is positive and one of the eigenvalues is negative, then we have what we call a saddle. So if one of the eigenvalues is positive and the other one is negative, then the equilibrium is a saddle. I'll point out it's considered unstable. It looks, again, similar setup. We have our first eigenvalue along this red eigenline, and our second eigenvalue along this other eigenline. I should again say, I'm drawing these very generically, right? They really could point in kind of any combination of directions that both went through the origin. They could be perfectly perpendicular or really close to each other. Lots of things can happen. But in this case, we're getting pushed away in the red direction, but we're getting pushed towards the origin in this green direction. So if you start anywhere other than on the green eigenline, like if we start here, we kind of get pushed in, but then eventually we get pushed away by this red one, or like that, or like that, or like that. Could be stable if our initial condition starts on the eigenline associated with the negative eigenvalue. But it's kind of like trying to ride the top of a ridge. If you're right on top, you're not going to fall out of the side. But as soon as you like just tip over one side slightly, you far and away you're gone. So these are the three things that can happen with real eigenvalues. Either both positive, both negative, or one of each. And the only stable one is when they're both negative. We'll see a similar condition for stability or instability when the eigenvalues are complex. The stable and unstable part really, really depends on whether the real part is positive or negative. So just like here, when both the eigenvalues are real and positive, we get instability. We'll see later on that if you have a complex eigenvalue where the real part is positive, you get instability. Similarly, when they're both negative, you get stability. And we'll see later on that if you have a complex eigenvalues where both real parts are negative, you also get stability. It's just that instead of being a node where you're just like kind of pointing out or pointing in, kind of like a spider web, you're spiraling out or spiraling in when it's a complex eigenvalue. And we'll definitely get there eventually. So let's look at some examples, because while it's fine to talk about what's generically happening, it's better to see some examples. So let's see here. Also, as usual, if you have questions, you're welcome to ask them. So let's look at this first example. So oftentimes when we get to this stage of the game, we stop kind of writing out the whole thing. Instead of saying we have a system of differential equations where dx1 dt equals something times x1 plus something times x2, and dx2 dt equals something times x1 plus something times x2, we say instead something like the following. If dx dt is equal to a times x, and A is a 2 by 2 matrix, analyze the stability of the equilibrium 0, 0. And then they just tell you what A is. So in the first example here, A is the matrix -4, 2, -5, 3. Now, even though we didn't write the whole thing, we know that this actually means you have two differential equations, right? This really means, although we don't need to write it down, but this means that we have dx1 dt equal to negative 4 times x1 plus 2 times x2, and dx2 dt equal to negative 5 times x1 plus 3 times x2. I'm not saying you should write this down. I'm just saying when you see a two-vector matrix like this, you should understand that we're talking about this system of differential equations, right? Every time from now on. The two-vector matrix really, if someone says, here's your matrix, you're like, okay, they're talking about this system here every time because that's what we are meaning with it until things get more complicated. So we don't need to write down any of that though, because all they've asked us to do here is analyze the stability, meaning tell me, is it a sink, is it a source, or is it a saddle? So really tell me, what are the eigenvalues doing? Well, there's a lot of ways to find the eigenvalues. I am pretty, I don't know, I feel like I adhere to the usual way of doing it, which is finding the determinant of a minus lambda I and then multiplying it out. So if it was me, I'd probably start with determinant of, and I would just jump straight to writing negative 4 minus lambda, 2, negative 5, 3 minus lambda. And then multiplying it out, so you get the product of the diagonals, negative 4 minus lambda times 3 minus lambda, minus the product of the off diagonals, 2 times negative 5. And setting that equal to 0 and solving it. It's not too terrible to do. You're going to get, let's see, lambda squared minus 3 lambda plus 4 lambda minus 12 plus 10, which becomes lambda squared plus lambda minus 2, set that equal to 0. And this one happens to factor. We get lambda plus 2 times lambda minus 1 equal to 0. So our eigenvalues are lambda equal to negative 2 and lambda equal to positive 1. Since they're opposite signs and both real, well, I should say, you can only really talk about the signs if they are both real. You can't really say a complex number is positive or negative. But since these are both real and have opposite signs, that means we have a saddle. We didn't do anything else. We're not asked to do anything else. We don't have to find the eigenvectors. We don't have to find the solution. All we've been asked to do here is just classify what the system looks like. Exactly what he said. If you're classifying, well, I should say, you might not even solve for the eigenvalues. Sometimes you can get away with doing less, which is kind of interesting. So, yeah, so I will say this is where I get kind of like, I ask myself, which way is the easiest way to do this? And it really kind of depends on your perspective. Some people prefer doing it this way because it's always kind of the same process every time. You're like, okay. But there are other ways to find the eigenvalues. I just, right, like 10 minutes before class, posted a video that one of the students shared with me last week about another way you can find the eigenvalues, which is, I think, pretty slick, but it requires you learning an extra thing. So maybe you want to do it that way. I don't know. You can check it out. I would encourage you to check it out. I think it's neat. I'm probably not going to show it to you that way because it's something different that we don't usually do, but it's also fine. I will show you one other way though, because I think there's another way of doing this that's worthwhile. So let's look at another example. Another example? Yeah, let's look at another example. So let's say we have the following same question, but now our matrix is 6, negative 4, negative 3, 5. One way of dealing with this, instead of doing what we just did, in fact, we're going to do it both ways here. I'm going to talk about two things. Is we're going to find the trace of A, which we often label as tau, and the trace is just the sum of the diagonal elements, which is 6 plus 5, which is 11, in this example. And the determinant of A, which we label as capital delta, or just a triangle, is 6 times 5 minus negative 4 times negative 3, which is going to be 30 minus 12, which is 18. Okay, we're going to come back to that in a little bit. As long as I'm not making, yeah, okay, cool. So now we're just going to do things the usual way. we're going to say that the determinant of a minus lambda I is equal to the determinant of 6 minus lambda, -4, -3, 5 minus lambda. Multiply the whole thing out. You get 6 minus lambda times 5 minus lambda minus -4 times -3. So we end up getting, let's see here, negative lambda times, you're always going to get lambda squared every time you do this, right? It's always going to happen. And then you're going to get a -5 lambda and a -6 lambda, so minus 11 times lambda, and a plus 30 minus 12. This ends up equaling lambda squared minus 11 lambda plus 18. Or something that's always true for a 2 by 2 matrix is it's always going to be equal to lambda squared minus whatever the trace of your matrix is times lambda plus whatever the determinant of your matrix is. Kind of neat. So one way to go about doing this is what I think of as the easy way, or the typical way. You can just factor this if it factors, right? This is going to factor as lambda minus 9 times lambda minus 2, which is clearly going to give us lambda equal to positive 9 and positive 2. So we know for sure both eigenvalues are positive, meaning we are an unstable node. So right here, both positive. We have an unstable node, also called a sink. Sorry, also called a what? A source, right? A sink, everything goes into. That's the stable one. The source, everything emanates from. That's the unstable one. We're pushing away, not going in towards. But I want to talk about a little bit more, another way you could see this, just for 1 second. Again, I should say, you should do this whichever way is easiest for you, right? Whatever way it is easiest for you to solve this quadratic equation is the way you should do it. Sometimes one way is easier than another. Also, no, we're not there yet. No, also nothing. So another way to think about this is you could just take this equation, this very generic equation that would work for finding the trace and determinant of any 2 by 2 matrix, and use the quadratic formula for that. And say, okay, well, the solutions are going to be lambda equal to negative b, so that's the negative of my trace, plus or minus the square root of my b squared. Well, my b is the coefficient of lambda, so that's my negative trace squared, minus 4 times a times my c is my delta, or my determinant, all divided by 2 times a, which is just 2 times 1. So here's what I think kind of interesting. You can rewrite this as just the trace plus or minus the square root of the trace squared minus 4 times the determinant, all over 2. Okay, so here's what I think is kind of neat. Observation 1. If your determinant's negative, sorry. So if the determinant of your matrix is negative, automatically a saddle. Every time. Why would that be true? Well, let's take a look here. If our determinant's negative, that means we're going to have tau squared minus a negative number. Or in other words, you're going to have something that is larger than tau squared. So if you add something to tau squared and then take the square root of that, it's going to be bigger than tau, whether or not tau is negative. So I just want to point out, that's going to mean that the square root of tau squared minus 4 times delta is going to be bigger than the absolute value of your trace. But then you have a number over here, and it might, so I'll say again, this number, this tau could be positive or negative. But then you're going to add something that's bigger than it and subtract something that's bigger than it. So if you took like -5 and added 7 and subtracted 7, one of those would be positive and one of them would be negative. Let me say it again. Take any number. Take another number that is bigger than its absolute value. So I picked, just for just making stuff up, I picked tau equal to -5. And then I said, okay, a number bigger than that, 7. I should say a number bigger than its absolute value. So 7 is bigger than the absolute value of -5. True story, right? So then if you take this number tau and you add or subtract a number that's bigger than its absolute value, you're always going to end up in a spot where one of the outputs is positive and one of the outputs is negative, right? If this is -5 plus 7 is for sure positive, -5 minus 7 is for sure negative. Or if tau was just regular 5, 5 plus 7 is positive, 5 minus 7 is negative. No matter where you start, if you have a number, whether it's positive or negative, and you add or subtract something that is larger than it in absolute value, you're going to end up with a 1 positive and 1 negative. Always going to happen if that determinant of your original matrix is negative. Why am I talking about this? You're like, we could just find the eigenvalues and not have to think about this thing. Well, later on, you might not have all the information you wish you had. Sometimes you're just told pieces of the matrix. You don't know the whole thing, and we're not quite there yet, but sometimes we have to deal with non-linear systems of differential equations, and then we're kind of going to see what's happening around a point. And so sometimes you just say, well, I know a little bit. I know the determinant's negative, cool, it's a saddle. Or I know the determinant's slightly positive and some other stuff. I know it's either a source or a sink locally. So that's kind of why we're talking about maybe seeing it this other way. And I kind of ran out of the room here, unfortunately. So I'll say 2 more things. Second thing I want to point out here is if your determinant is positive, well, then you have lots of options. Really, almost anything can happen. So let's think about for a second here. If we look inside here, well, we were only dealing with real eigenvalues right now, right? We haven't talked about the complex ones, although they're on the horizon, they're coming up. But if your eigenvalues are going to be real, then your discriminant has to be positive, right? The thing you're taking the square root of has to be greater than or equal to 0. So we need tau squared to be bigger than 4 times delta. Or for whatever reason, I don't know why, people prefer to write this as delta has to be less than tau squared divided by 4. Same thing, just written in a slightly different way. So if those 2 things are true, then 4 things can happen. Well, no, sorry, 2 things can happen. Then thing 1, if your trace is positive, well, if your trace is positive, then both eigenvalues are going to be positive. How are they both going to be positive? Why can't they get one positive, one negative? Well, because I'm adding or subtracting something that is smaller than it, right? If I have tau squared and I'm subtracting something that's positive, it's getting smaller, and then the square root is going to be smaller than the original number. It'd be like 5 plus or minus 4, both positive. Or -5 plus or minus 4, both negative. So if this thing in here, right, if your delta is positive, that means this whole thing got smaller. So that means you have whatever sign this is the sign that's going to carry the day. If this is positive, both positive. This is negative, both negative. So if tau is positive, that means your both eigenvalues are both positive and you have an unstable node. And similarly, if your trace is negative, then both lambdas are negative and you have a stable node. Do I do it this way? I absolutely do not. But do I need to show it to you? I kind of feel like I do. So I wouldn't normally do it this way in a typical case, right? If I was given a matrix, I would just start off doing it the usual way. So for example, so actually back to this example though, just to point out. So our example, which was A equal to 6, -4, -3, 5, where our trace was 11 and our determinant is 18. Well, we're certainly in the case where our determinant's positive. And if we compare these two, well, this is kind of gross. Our determinant's 18. Is 18 smaller than 11 squared over 4? Right. Who wants to answer that question? Not me. But it is. 11. Oh, no, it's not. It's not? Is it not? Did I do the wrong thing? No, I don't think so. See, this is why I don't do it. I'm like, is it? I don't know. Maybe. It could be. 121 divided by 4. Oh, yeah, it's definitely, yeah. 18 is like what? 72 over 4. Okay, so yes, it is. Right, you have this, right, already I've done more mental math than I care to. I should have just done it the other way. But then we can say, cool, since this checks out and our tau is positive, that means we have an unstable node. Kind of feels like more work than it's worth. It usually is, but not always. So it's good to know that there's multiple ways of doing something. But again, I would usually probably default to finding the eigenvalues and eigenvectors the typical way. The problem becomes sometimes that means going and using the quadratic formula. So let's look at one more example here. I started numbering things the wrong way. Sorry. This was not 2. This is, yeah, sorry. My numbering is all over the place. Sorry about that. If our matrix was, say, -3, -1, 1, -6. Things aren't going to be pretty here. That's okay. So let's go ahead and find it. Our eigenvalues, determinant of a minus lambda I. I'll say it again. Every time you do this, you're just subtracting lambdas from the diagonal spots and then doing the usual calculation. -3 minus lambda, -6 minus lambda, minus -1 times 1. Now we are going to write this out. So we're going to get lambda squared plus 6 lambda plus 3 lambda is plus 9 lambda. And then plus 18 plus 1 is plus 19. And looking at this, you can probably see that this does not factor, right? There's no good way. There's only one way of multiplying to 19, 1 times 19, or -1 times -19. And that definitely doesn't add up to 9. So here you'd have to use the quadratic formula anyway. So here our eigenvalues are going to be -9 plus or minus the square root of 9 squared minus 4 times 1 times 19 all over 2, which is going to be -9 plus or minus the square root of 81 minus 76 all over 2. Okay, so are they both negative? Are they both positive? Or are they one of each? -9 is -9. Square root of 5 is about, what's it for sure smaller than? Definitely smaller than 3, right? It's for sure smaller than the square root of 9. -9 plus 3 is -6. -9 minus 3 is -12. They're both negative. And again, we're seeing the thing we saw before where if you're adding or subtracting something that is smaller in absolute value than the thing you started with, you're not going to be able to get a change in sign. They're both going to be negative, or they're both going to be positive. So these are both negative, meaning we have a stable node or a sink. Yeah. Let me give you an easy one. And I expect that all of you should be able to tell me the answer by now. Why would it be so easy? The 0 up there. So I want to point out the 0. So I'll just say this matrix I'm about to write would not be easy. You'd have to work to find the eigenvalues there. But here, all of you should be able to tell me what the eigenvalues are. The eigenvalues are 4 and -5, which means we have what? A saddle. We also could have seen this by saying, hey, the determinant of our matrix A is 4 times -5 minus 0, which is -20, which is negative. And when the determinant's negative, it's always a saddle. One more fun fact. This probably doesn't get taught in your class, but I think it's worth knowing anyway. So, and this fun fact does come up in that video that I posted in Canvas earlier today. The determinant of your matrix is equal to the product of the eigenvalues. So whatever the eigenvalues are, their product is equal to the determinant. And the trace of the matrix is equal to the sum of the eigenvalues, which probably seems relatively obvious for this matrix, right? The eigenvalues add up to -1, and the trace is the same as adding up the eigenvalues, which is -1. Similarly here, the eigenvalues multiply to -20, and the determinant is -20. But it's also true in the previous matrices. If you look over here for a second, now that's not a great example, James. If we look over this previous one for a second here, where'd you go? Where did you go? Gosh, where's my first example? The one I want, yeah. If you look at this example here, the trace of this matrix is -1, and the eigenvalues add up to -1. And the determinant of this matrix is -12 minus 10, sorry, plus 10, which is -2, and the eigenvalues multiply to -2. That is always true. It's actually true for matrices of any size, but we only care about 2 by 2s. But it's true that for matrices of any size, all the eigenvalues multiply to the determinant, and all the eigenvalues add up to the trace. It's kind of neat. It is a useful piece of information sometimes. Okay, how much time have I got left here? Sure. Questions, comments, thoughts? Okay. Sure, let's do that. So I would say this, not the trace determinant stuff so much, but definitely memorizing that the conditions for the eigenvalues and what kind of stability that gives you is super important. So I'm going to say it again. Stability criteria. If both eigenvalues are positive, unstable node. Both eigenvalues negative, stable node. And again, the node part just means everything's kind of pointing inward or pointing outward. It doesn't have to be like straight pointing in. It could be like kind of have some curviness to it, but it's not like spiraling around. And then thirdly, one of each. One positive, one negative. We have a saddle. But then, as you might be aware, not every quadratic equation has real solutions. So let's look at another example. A new example. What about the following system? dx1 dt equal to, sorry, I'll just write the whole matrix here. Fine. dx, apologies, dt is equal to the matrix -1, 2, -3, -1 times the vector x. That's just an x, not an x1. Sorry for my terrible penmanship. So again, this represents a system of 2 equations, 2 unknowns. I could write them out like I was trying to. We don't really need to, but it's good to remember where these things come from. So we know that we have these 2 equations. dx1 dt equal to -1 times x1 plus 2 times x2. dx2 dt equal to -3 times x1 minus 1 times x2. Now we're going to talk about finding the solutions to this system. Well, things look very different now. Because if we try to find the eigenvalues, determinant of a minus lambda I is going to be the determinant of -1 minus lambda, 2, -3, -1 minus lambda. Something worth pointing out. If both of your diagonal elements happen to be the same, you can solve this with a little bit less work. Here's what I mean. I have -1 minus lambda times -1 minus lambda minus 2 times -3 equal to 0. And normally what you've seen me do every time is multiply this out and then rewrite it with all one thing and then solve. But in this case here, since I have a -1 minus lambda times another -1 minus lambda, I could just write -1 minus lambda squared plus 6 equals 0. And then I could just bring the -6 over to the other side and write it as -1 minus lambda squared equal to -6. And here's where things do get a little bit unfortunate. We have to square root that -6. So we're going to get -1 minus lambda equal to plus or minus the square root of -6. And then we can rewrite this as, I would probably say, sure, negative lambda equal to +1 plus or minus the square root of -6. And then multiplying both sides by -1, we get positive lambda equal to -1. If you multiply a plus or minus by -1, it's still a plus or minus, just that's all there is to say, really. So, right, you're still adding one and subtract. You can say I'm adding the -1, subtracting the positive, and subtracting the -1, which is the same as adding the 1 and subtracting 1. So same thing. So this is plus or minus the square root of -6, which we're then going to rewrite as lambda equal to -1 plus or minus I times the square root of 6. A few things to say here. When your eigenvalues are complex, they will always come in complex conjugate pairs. So there'll always be a real part plus or minus an imaginary part. Language differs sometimes. Some people say the imaginary part is √6. Some people say the imaginary part is I times √6. Either way of saying it's correct. We mean the same thing. Just sometimes people say it differently. I don't know why. There's not an agreed upon particular name here. So what's happening here? Well, geez. So we're going to go back to our general solution. Yeah. And say, well, just like before, our solution is going to look something like the following. C1e to the lambda 1 t times v1 plus c2e to the lambda 2 t times v2. Okay, so, but now we've got a lot more mess because our lambda 1 is this deal here, and our eigenvector is also kind of funky. So let's find the eigenvector. So I keep looking at the clock like, how much time do I have to really say this? Okay, so this is the moment where I would find the eigenvector the other way than I usually do. Here's what I mean. So normally, and we haven't done today yet, but normally I have found the eigenvector typically by saying your matrix times your vector equals the eigenvalue times your vector. So I would typically do this. A times the unknown eigenvector equals lambda times the unknown eigenvector. In this particular example, that would mean we'd be writing down the matrix -1, 2, -3, -1, multiplied by the eigenvector we're trying to find, equal to -1 plus, and we'll do the plus one first, plus I√6 times the unknown eigenvector we're trying to find. And if you look at this equation, either equation I use, if you look at the system of equations, either equation I use is messy. The first one would be -1 times x plus 2 times y equals -1 plus I√6 times x. It's just kind of dicey. So what I would suggest is actually doing it the other way. instead of doing it this way, I prefer when my eigenvalues are complex to do it as A minus lambda I times my unknown eigenvector equal to the 0 vector. So in this case, here's what that's going to mean. We still have some kind of grossness when we subtract things here, but it's going to be fine. So we have -1 minus -1 plus I root 6 to -3 and -1 minus -1 plus I root 6 all times xy equal to 0, 0. Now, I'm going to simplify these a little bit here. I'll point out that this part here is just going to be -1 plus 1 is 0, so this is going to be -I root 6, and so is this. Here's my point. I think it's much easier to look at this first row times xy equal to 0. So -I root 6 times x plus 2 times y equal to 0. And then it's very, very straightforward to isolate y. 2y is just going to be I root 6 times x. And to find the eigenvector, we can do the same thing we used to do, which is to say x is the y coefficient and y is the x coefficient. So my eigenvector is going to look like y is I root 6 and x is 2. So x is 2 and y is I root 6. We could have also gotten there from here, and I shouldn't like pretend. It's not that much worse up here. For me, I don't know. This just looks worse to me for some reason. But it's not, right? You could certainly add x to both sides and get 2y equal to I root 6 times x. I just feel like sometimes this is messier. And maybe sometimes the eigenvalues are even worse because you have like a denominator or a fraction. It's just not pretty. That said, as is typical, either way is fine. You can pick. Now, here's the beauty of this. We've already found both eigenvectors. I know we didn't do the work, but let me point out, if my other eigenvalue is -I minus I root 6, well, I can throw in a minus sign there, a minus sign there. That'll change this to a plus I root 6, that to a plus I root 6, and it'll change my equation to plus I root 6 times x equal to plus 2y equals 0, or 2y equal to negative I root 6. So my other eigenvector, right, if my first eigenvalue is -1 plus I root 6, and my eigenvector is 2 I root 6, my second eigenvalue is -1 minus I root 6, and the associated eigenvector is the same as this eigenvector. You just change the sign of the imaginary part into -I root 6. And that idea is always true, that once you found your eigenvalues as complex conjugates, which they always are, then the eigenvectors, the complex part, the imaginary part, just changes sign. So in this vector here, wherever you have an I, change it from positive to negative or negative to positive. Always works. And then the real answer is you don't even have to find the second one. I wanted to point out that finding the second one is easy, but when we start talking about writing out the whole solution to this, which is kind of terrible, but we'll do it. Finding the whole solution to this, you only need one of these eigenvectors. And we almost always pick the one where it's the positive part here. Right, you pick lambda equal to this one where it's positive, and then the associated eigenvector, whatever happens to be. Because I don't know why. Because you have to pick one. So next time we'll talk about how the actual solution to a system with complex eigenvalues works. It's kind of a pain in the butt, but we will work through it. And definitely Lee's class will make you do it for sure. Varn's class, I'm not sure if he will or not, but definitely the last 2 times Lee has taught this, he has for sure asked about a system with complex eigenvalues and so on and so forth. So we will get to that on Wednesday. I have office hours over in drop-in. Feel free to come.